This is another example of solving to find the DC values for the currents and the voltages in a circuit. So to start this, you can take a Thevenin of the circuit that has a little bit more complexity to it, and in this case I'm going to do this side right here, and I'm going to find the Thevenin equivalent, which is Vx. And I can do that by node voltage, or noticing that all of the current that goes through here also goes through here. Either way, if I do node voltage, I get a minus 2 milli plus VTH over 50/50 equals 0, and I can solve that for a VTH, which is equal to 10.1. volts. RTH is going to be from this node to ground, so I can go through this branch and this branch, but this current source becomes an open. So RTH for the equivalent circuit is just going to be 50/50. So now my circuit is going to just look like this. And it's going to be 10.1 volts, which is plus to minus, compared to ground, 50/50, and IB is going to go through it here. And then I also have a 0.7 volt drop at this location. So, oh, that was supposed to be white. So my new circuit using that Thevenin ends up looking like this. So with our new circuit here, I can solve for the DC values by taking a loop from the base through to the emitter. So that loop, I have a plus to minus here, and then the current is going to be IE plus to minus. So I would have a plus, minus, 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 plus, and then this is also to ground here, so I get a plus. And so I have a plus 10.1 minus IB 50/50 minus 0.7 minus 1 minus IE 9.95K plus 6, and then a plus 5.6. That's a 5.6, and all of that is equal to 0. And then I use the active region relationship of IB is equal to IE divided by beta plus 1, and I can plug that into this and then solve for IE, and that will yield an IE value that is equal to 2 milliamps. So IE is 2 milliamps. And then IB will be 19.8 microamps. And IC is beta IB. And so get 1.98 milliamps. The voltages can be found for VB is going to be plus 10 minus 10.1 minus the IB 50/50, and that's equal to VB, and so I get a value for VB of 10 volts, and then I can take VE is VB minus 0.7, so I get 9.3. I can also find VE from the loop from ground up to VE. That would be a minus 5.6 minus 6 plus IE 9.95K plus 1 will give me VE value. VC is going to be a plus 20, and then IC is going to be here, so I get a plus to minus, and so a minus IC2K and a minus 1. So again, that was plus 20 minus IC2K minus 1, and that yields a VC that's equal to 15.04. And so VC at 15.04 is going to be greater than a VB of 10, so therefore it is active. So the other part of this problem asked what will be the maximum input for V5, which you notice V5 is here, if the following is the result from an AC sweep. So this is the Bode plot simulation of this circuit, and so you can see how it goes up and comes back down, and the flat region is the range of operation that it can operate in, and it will have a flat value. And in this case, you can see that it's measuring in at 15 volts per volt. So that means that the AC gain for this circuit is 15 volts per volt. So the output, which is considered at VC4, because it says it's VC4 over the input, is 15 volts per volt. We notice here that the voltage VC can't be higher than the supply voltages on this side, and in this case it's 19 minus 1 would be the max that we could get there. So that is 19 volts would be the max we could have there. So VC has to maintain a range between VB and the supply voltage. So currently VC, that's VC total, which would be the AC combined with the DC. So remember that VC is a DC value plus an AC value. So the DC value was about 15 volts. So the supply max would be 19 volts, and VB was found to be 10 volts. So the AC portion that could be added on here, it would be to take off 5 volts to get to VB, and it would be to add on 4 volts to get to the supply. So the lower value out of that comparison is 4 volts. And so we're going to limit the AC portion to be, again, the smaller value that can be added to this, because the smaller value will be more limiting. So again, that's the supply voltage was 19, so 15 plus 4, and then VB was 10, so there's a difference there of 5. So the AC would be a minus 5. And remember, the AC is a plus minus value. So the lower value we said would be 4 volts AC. So this would be the max that V out can be. So with a gain of 15, the maximum V out would be is 4. Solving that circuit or that equation for Vn would mean that Vn comes over to this side and Vc4 divided by 15. In this case, that would be 4 over 15 would be your max input that you could have.